Hello students, welcome to the lecture on Indices and Logarithms, and after this lecture we will be able to learn the following objectives. Discuss laws of indices, learning about definition of logarithm, define logarithms to base 10, describe multiplying and dividing numbers using logarithms. Let's start with the concept of indices and logarithms. When a factor is multiplied by itself a number of times, we can use powers to express this operation in shorter form. For instance, the operation 2 into 2 into 2 may be expressed as 2 raised to 3, where 2 is the number being multiplied and 3 is the number of times we are multiplying it. Thus 2 is known as the base and 3 as the power, and we read 2 cubed as 2 raised to the power of 3. Another name for power is index, from which we get the plural indices. As we have seen that indices arise from multiplication of similar factors a certain number of times. Take for instance finding the area or the volume of a figure of side 3 cm. From the formula area equals to length into width and volume equals to length into width into height, the area is given as 3 into 3, which is equal to 32 cm square, and the volume is given as 3 into 3 into 3, which is equal to 33 cm cube. Note that even the units are given the same index since they are also multiplied together a given number of times. Indices are used to describe repeated multiplication. This is why they are very useful in science when writing very large or very small numbers. For example, the size of the HIV virus, about 400 nanometers or 4.0 into 10 to 7 meters, or distance of the sun from the earth, about 145 million kilometers or 1.49 into 108 kilometers. Let us now discuss the laws of indices. The laws of indices are concerned with addition, subtraction, multiplication and division of powers of similar numbers such as the area and the volume of the figure. We shall look at these laws in regard to the four operations. Law 1. Adding indices, multiplying products of similar factors. Find the product of 3 into 3 into 3 and 3 into 3. Then introduce the indices for both groups and show how both approaches lead to the same result. Activity 1. Work out the product of 3 into 3 into 3 and 3 into 3. We see clearly that 3 has been multiplied 5 times, that is 3 into 3 into 3 into 3 into 3. Since in the first case 3 has been multiplied 3 times, we can write it as a 3 cube, and the multiplication in the second case can be written as 3 square. Use the new expressions to rewrite the original expression, that is 3 cube into 3 square. From the expressions 3 cube equals to 3 into 3 into 3 and 3 square equals to 3 into 3. We see that 3 cube into 3 square equals to 3 into 3 into 3 into 3 into 3, which is equal to 3 into 3 into 3 into 3 into 3. But as we saw, 3 into 3 into 3 into 3 into 3 equals to 3 to the power 5, since 3 is multiplied 5 times, which is equals to 3 to the power cube into 3 to the power square, which is equals to 3 to the power 5. If we observe closely, we will notice that the powers on the left hand side of the equal sign add up to the power on the right hand side of the equal sign. That is 3 plus 2 equals to 5. This means that when similar factors or when similar numbers are multiplied, the result is always that number or factor with its index as the sum of their indices. Thus, if a factor or any natural number, then the product of any two of its multiplers am and an is given by am into an, which is equals to am plus n, where m and n are the indices. Law 2. Subtracting indices, dividing products of similar factors. Find the quotient of 3 into 3 into 3 and 3 into 3. Then introduce the indices for both groups and show how both approaches lead to the same result. Activity 2. Divide 3 into 3 into 3 by 3 into 3. We see clearly that the 3's in the denominator cancel out 2 of the 3's in the numerator, leaving only 3. Since in the first case 3 has multiplied 3 times, we can write it as 3 cube, and the multiplication in the second case can be written as 3 square. Use the new expression to rewrite the original expression, that is 3 cube divided by 3 square. We can say about the two expressions. Again, from the expression 3 cube equals to 3 into 3 into 3 and 3 square equals to 3 into 3, we see that 3 cube divided by 3 square equals to 3 into 3 into 3 divided by 3 into 3, which is equals to 3. But as we saw earlier, this means that 3 to the power 3 cube divided by 3 square equals to 3 to the power 3 minus 2, which is equals to 3 to the power 1. Here we see that the powers on the left hand side of the equal signs are subtracted to obtain that on the right hand side, that is 3 minus 2 equals to 1. Law 3. Multiplying the indices. Raising a product of similar factors to a power. Find the product of 3 square and 3 square. Then raise the first expression to the power of the second expression to show how both approaches lead to the same result. Activity 3. Work out the product of 3 into 3 and 3 into 3. We see clearly that 3 has been multiplied 4 times. That is 3 into 3 into 3 into 3. Since in the first case 3 has been multiplied 2 times, we can write it as 3 square, and the multiplication in the second case can be written as 3 square. Use the new expression to rewrite the original expression, that is 3 square into 3 square. We see that 3 square has been multiplied with itself once, that is 3 square into 3 square. By expansion, 3 square into 3 square, which is equals to 3 into 3 into 3 into 3, 3 square into 3 square equals to 3 to the power 4. Now what if we multiply 3 square twice? 3 square into 3 square into 3 square. By expansion, 3 square into 3 square into 3 square equals to 3 into 3 into 3 into 3 into 3 into 3. 3 square into 3 square into 3 square equals to 3 to the power 6. From the examples above, we see that 3 square into 3 square equals to 3 square to the power square, which is equal to 3 square into 2, and 3 square into 3 square into 3 square equals to 3 square to the power cube, which is equal to 3 square into 3. We see that the powers on the left hand side are multiplied by the number of times they appear to give the power on the right hand side. Thus, if a multiple of a factor or any natural number is am is raised to the power n, then the result is given by the factor a raised to the power mn. Am to the power n equals to am into n, or am to the power n equals to amn. Law 4. Dividing indices. Dividing roots of a product of similar factors. Law 5. Negative indices. When the divisor is larger than the dividend. Law 6. Zero index. Dividing two similar products or factors. Law 7. Indices of different bases with a common power. Did you know the term logarithm was first used by a Scottish mathematician, John Napier, 1550 to 1617, in reference to the power or index of a real number? Now, moving on to the next topic, we will study the definition of logarithm. Logarithm is believed to have come from two Greek words, logo meaning ratio and arithmos, which means number. The name therefore suggests that he must have used ratios to obtain the powers or indices of numbers. Given that 10 square equals to 100, the logarithm or ratio of the numbers 10 square and 100 is obtained as follows. Step 1. Introduce logarithms on both sides, that is, log 10 square equals to log 100. Step 2. Separate the power from the base, that is, 2 log 10 equals to log 100. The translation reads, twice the power of 10 equals once the power of 100. This literal translation is obviously not clear. A better translation reads, the power of 10 is twice that of 100. Step 3. Divide through by log 10 to obtain the ratio, that is 2 log 10 or log 10 equals to log 100 or log 10. This gives 2 equals to log 100 or log 10. This could be read as the ratio of the powers of 100 and 10 is 2:1. Step 4. Simplify the ratio, that is 2 equals to log 10 into 100. Here 10 is the base or the factor when the number is factorized to obtain power, and 100 is the multiple or the product. In general, given that a to the power b equals to c, where a is the power base, b is the power and c is the product, we may say that log a to the power b equals to log c, b log a equals to log c, b equals to log c or log a, and b equals to log ac. Note that a is the base in both the exponential equation and the log equation. Note also that b and c switch places when we change from index form to log form. We have seen that logarithms can be obtained in any base. After all, a logarithm is a ratio of powers or indices of real numbers, be it positive or negative. But just as we saw with counting systems, base 10 has been identified as the most ideal base to use when working with logarithms. It is for this reason that we have to convert all logarithms that cannot be evaluated in other bases into base 10. Consider a problem such as x equals to log 8 into 16. It is obvious that we cannot evaluate this problem in base 8 because 8 is not a root of 16. This means that x the power of 8 is not a whole number but a ratio of two numbers or a decimal number. Finding logarithms in base 10. Step 1. Use the fourth law of logarithms to write the RHS as a fraction, that is x equals to 8 log 16, which is equal to log 16 or log 8. Step 2. Use the log tables to find the values of the numerator and the denominator. These tables show the logarithms of the factors in the standard form p into 10 to the power n, where p is the leading factor and n is the power of 10. It is for this reason that the values in the table lie between 1 and 10. That is, 1 is less than equal to p, which is less than 10. So the numbers in the tables range from 1.00 to 9.99, although the decimal point is not shown in the table. Finding logarithms of positive numbers less than 1. When positive numbers less than 1 are expressed in standard form, the power of 10, the characteristics, is given as negative. This is because the decimal point is moved past the given digits towards the right when trying to obtain a leading factor in the range of 1 to 10. Note that the logarithm or the power of the leading factor, the mantissa, is positive since the number is positive. Consider a number 0.01. In standard form, the number becomes 1.0 into 10 to 2. The logarithm of the leading factor log 10 1.0 equals to 0, implying that log 10 1.0 into 10 to 2 equals to log 10 1.0 plus log 10 10 to 2. Log 10 into 100 into 10 to 2 equals to 10 to 2 plus 0.00, which is equals to 2 plus 0.00, which is equals to 2.000. Notice how we write a negative characteristics. We put a bar on top to signify that the power of 10 is negative or that the actual number that was expressed as a logarithm is less than 1. We read a negative logarithm as a bar of the number, example, bar 2.0. We have seen that the laws of logarithms make use of multiplication and division. Therefore, we can use logarithms to multiply and divide numbers. Multiplying numbers using logarithms. According to the first laws of logarithm, log 2 into 3 equals to log 2 plus log 3. So we can easily multiply numbers according to the first law of logarithms using the steps outlined here. Activity. Find the product of 2 and 3 using logarithms. Step 1. Express the product as a sum of logarithms, that is, log 2 into 3, which is equals to log 2 plus log 3. Step 2. Find the logarithms of the factors in the sum using the log tables. That is, log 2 equals to 0.3010 and log 3 equals to 0.4771. Step 3. Add the logarithms obtained. That is, 0.3010 plus 0.4771 equals to 0.7781 or 100.3010 into 100.4771 equals to 100.30100 plus 0.4771, which is equals to 100.7781. Step 4. Look for the logarithm obtained as a sum in step 3 from the log tables. Then read off the first values, first along the row and then along the column, intersecting at this point. Step 5. Add up the values obtained. The sum is the required number. So 100.7781 equals to 6.00. A quick check shows that 2 into 3 equals to 6. Example, evaluate 245 into 35. Solution, using the standard form, 245 becomes 2.45 into 102. 35 becomes 3.5 into 101. Applying logarithm gives log 245 into 35, which is equals to log 245 plus log 35, which is equals to log 2.05 into 102 plus log 3.5 into 101. Log 2.45 plus log 102 plus log 3.5 plus log 101, which is equal to 0.3892 plus 2 plus 0.5441 plus 1, which is equals to 3.9333. Now, expressing the sum of logarithms as powers of 10 gives 103.9333, which is equal to 103 into 100.9333. Using log tables, 100.9333 lies between 100.9330 and 100.9335. So we find the average, that is 0.9330 plus 0.9335 divided by 2. But 100.9330 equals to 8.57 while 100.9335 equals to 8.58. So their average is 8.57 plus 8.58 equals to 8.575. Thus we have 8.575 into 103 or 8575. A quick check shows that 245 into 35 equals to 8575. Note that we use a lot of approximation and estimation while dealing with logarithms, especially while trying to find the leading factor in the standard form. Using logarithms, we can also divide numbers using logarithms and the laws of indices. Observations of logarithm. It should be noted that the two equations a to the power x equals to n and x equals to log an are only transformations of each other and should be remembered to change one form of the relation into the other. The logarithm of 1 to any base is 0. This is because any number raised to the power 0 is 1. Since a to the power 0 equals to 1, which is greater than equal to log a, 1 equals to 0. The logarithm of any quantity to the same base is unity. This is because any quantity raised to the power 1 is that quantity only. Since a to the power 1 equals to a, which is greater than equal to log a equals to 1. Note there are a few restrictions on the base. It should not be taken as 0 or 1 because a 0 raised to any power is meaningless and 1 raised to any power is 1 only. Nor can the base be a negative number, otherwise certain values will become imaginary. As regards the number n for which we find the logarithm, the restriction is that it should be a positive value not equal to 1. Did you know? The first use was suggested by John Napier, who invented logarithms to the base e equals to 2.71828. which is used mostly for theoretical mathematical purpose. Now in the end, let us summarize what we have learned in this lecture. The conversion of values into logarithms is, however, no problem since ready-made conversion tables are available for the purpose. The laws of indices are concerned with addition, subtraction, multiplication and division of powers of similar numbers such as the area and the volume of the figure. Logarithm is believed to have come from two Greek words, logo, meaning ratio, and arithmos, which means number. The logarithm of a number to a given base is the index or the power to which the base must be raised to produce the number, that is, to make it equal to the given number. When positive numbers less than 1 are expressed in standard form, the power of 10, the characteristic, is given as negative.